once again, and today I'm going to shoot a video regarding basically we are going through unit 2. Okay, so as I have already told you in the previous video that we will cover basically two main topics. So first topic was the fins, the extended surface, which I've covered in the previous video, and now this video will actually under the umbrella of transient heat transfer. Now transient heat transfer has two basic topics. One is the lumped parameter analysis, that is the analytical portion or the mathematical portion, and the other one is more of graphical. Yeah, mathematics is bit there, but it's more of a graphical analysis. I mean graphical method of solving the problems. Okay, but the checking parameter is different, so I will be going through all the parameters. So guys, so let's talk about the unit 2, and this is the transient heat conduction. Okay, so in transient conduction, temperature depends not only on position in the solid but also on time. So mathematically this can be written as T, means the temperature, is equals to T of x, y, z and tau. Tau is the time, it's written there. So typical examples of transient conduction are heat exchangers, boiler tubes, cooling of IC engine cylinder heads. So first of all, you might be thinking a question, what do you mean by transient heat conduction? Transient heat conduction is just the opposite of steady state conduction. We have already covered steady state conduction when I was deriving the conduction equations in various coordinates. So this I am just repeating it once again. Steady state conduction is a conduction where the heat doesn't change with time, okay, but transient, yes, it does changes with time, and this is the main and this is the most important thing that you will ever solve, because in each and every practical application you will never find it's a steady state conduction, because there are losses and losses actually increases with time. So definitely the value of heat either goes up or goes down as per the application. So generally the value of heat comes down because there are losses, and losses actually increase with time. Okay, so you need to take measures which will be taken up later on. So the typical examples of transient conduction, and see, they all are practical examples like heat exchangers, okay, boiler tubes, cooling of IC engines, cylinder heads. Okay, examples are continuing now, heat treatment of engineering components and quenching of ingots. What is quenching? Quenching is basically you just heating it in an oven, and then you are just putting that particular ingot immediately into the liquid oil, means cooled oil. So what happens? There is a sudden drop in temperature and the material gets harder. Okay, so this is basically quenching, and definitely you are seeing that the quenching is basically with the time you have actually changed the temperature. So this is a very, very, very important example of this particular topic, that is transient heat conduction. Heating of electric irons, definitely when you turn on your ironing machine, it is not already hot, so it takes time. So with the time the heat is adding up. So this is an example of heat addition. Heating and cooling of buildings, definitely during the daytime it is hotter, during the night time it is cooler. Okay, freezing of foods. Okay, lumped system analysis, Newtonian heating or cooling, this is the main topic for today's video. Okay, in lumped system analysis, the internal conduction, you just read these yellow parts very carefully. In lumped system analysis, the internal conduction resistance of the body to heat flow, L by Ka, and you know what is L by Ka. This is the conduction thermal resistance, as I have already shown this to you in my previous video shoots. So I am reading it once again. The internal conduction resistance of the body to heat flow, that is L by Ka, is negligible compared to the convective resistance, that is 1 by Ha. This I have discussed in my previous videos. Okay, so the temperature of the body no doubt varies with time. Okay, at any given instant the temperature within the body is uniform and is independent of the position, that is T is only now depending on the time. Okay, lumped system analysis, again continuing. Practical example of such cases are heat treatment of small metal pieces, measurement of temperature with a thermocouple or thermometer. Okay, when you are when you are down with a fever, you know that the thermometer mercury actually goes up very slowly and steadily. because the temperature doesn't shoot up like that. It takes some time. So definitely the time, the temperature is the function of time. So that is what we are dealing now. Okay. So practical examples of such cases are heat treatment of small metal pieces, measurement of temperature with thermocouple or thermometer, etc., where the internal resistance of the object for heat conduction may be considered as negligible. Okay. D analysis. Consider a solid body of arbitrary shape, volume V, mass m, density rho, surface area A, and specific heat Cp. Okay, this is the figure to be understood. This is any particular object. Okay, and these are the properties like m, v, rho, and t. To start with, at the initial time, that is tau is equals to 0. Tau is equals to 0 when you start the timer. Let the temperature throughout the body be uniform at T is equals to Ti. Okay, so at that instant, so this is having this temperature, that is T is equals to Ti. So at that instant means at tau is equals to 0, let the body be suddenly placed in a medium at a temperature Ta. Means suppose if you are taking a condition of quenching. Okay, just now I've explained you the condition of quenching, means the process of quenching, that's a heat treatment process, okay, to make the material harder. Suddenly you are dipping it in, suddenly the temperature has reduced. See, it is Ta. Suddenly it is being exposed to the ambient temperature or any temperature, that is Ta, and which is lesser than Ti, which is lesser than Ti. Writing an energy balance for this situation. So the amount of heat transferred into the body in interval d tau. D tau means the time interval. Okay, the amount of time that is taking from the body to cool from the temperature Ti to d tau to Ta. Okay, so tau is the temperature. So tau is the temperature of, we are calculating the time from, the reduction of temperature from Ti to Ta, or for that matter any temperature in between. Okay, so increase in the internal energy of the body in time interval dt will be HATA minus T tau dt is equals to mCp dt. This is the change in internal energy. This is the change in internal energy, and this is the convection. Okay, HATA minus T tau. Okay, so now since Ta is constant, we can write. So definitely what we can do is we can actually club it like this. Okay, we can actually club it like this because the Ta is constant. So when the Ta is constant, so this is what we can rearrange to, and then we get this equation, and this is a very important equation for this particular topic. So this HA by rho CPV, let's go ahead first of all integrating it. Okay, now we'll be integrating it just because we have this d terms right now, right? We have this d term. So if we integrate this, so after integrating we are getting natural log of this should be equals to minus HA tau by rho CPV. Okay, V is the volume actually. Okay, so finally what's happening is, now if we remove the natural log from this side, so it will be e to the power, okay, it will be e to the power minus HA tau by rho CPV. Now can you see this? There is a terminology, there is a term of time here. So all this thing should also have the unit of time. Okay, so let the surface, so all these things should also have a unit of time. So let the surface on the left be maintained at temperature T1 and the surface on the right is at temperature T2 as a result of heat being lost to a fluid temperature Ta flowing with a heat transfer coefficient Ha. Writing an energy balance at the right hand surface, it will be conduction is equals to convection. Okay, so now let's talk about criteria for lumped system analysis. So criteria for lumped system analysis. Okay, so let me just tell you one thing. This particular term minus HA by rho CV, this, if we write it like this, rho CPV by HA, this is called thermal time constant. This is a very important thing. This is a thermal time constant and it comes along with the tau, and its unit are also seconds. Okay. So this is nothing but conduction is getting equated to convection. Okay. Now criteria for lumped system analysis. So the criteria for lumped system analysis is basically when we rearrange that particular term, when we rearrange this equation, so we get like L by Ka by 1 by Ha. So L by Ka we all know that is resistance of conduction, and 1 by Ha we all know that is resistance of convection. Okay. So this term HL by K is a very important number. It's a dimensionless number, and this is termed as Biotz number. Okay. This is termed as Biotz number. It's a dimensionless number. So Biotz number Bi, and this is the checking criteria. This is the checking criteria that whether you will be applying lumped analysis or whether you will be applying Heisler's chart. So you will first of all, in any numerical, you will first of all check the Biotz number, and Biotz number's formula is HL by K, and it is actually the ratio of thermal resistance of conduction by thermal resistance of convection. And if the Biotz number is lesser than 0.1, the temperature gradient in the solid is small, and temperature can be taken as a function of time only. So this is 0.1 actually. Okay. So this is 0.1. Okay. Now note also that for Biotz number greater than 0.1, okay, greater than 0.1, temperature drop across the solid is much larger than that across the convective layer at the surface. So let us define Biotz number in general as Biotz number is HLC by K, and this LC is nothing but the characteristic length, and characteristic length is equals to volume upon area, and we know that volume is equals to area into length. It has been derived from the same formula. Okay. C is the volume upon area, where the H is the heat transfer coefficient between the solid surface and surroundings, K is the thermal conductivity of the solid, and LC is a characteristic length defined as the ratio of the volume of the body. Okay. So therefore this equation can therefore be written as HL by K. See this equation can therefore be written as HL by K into alpha tau by LC square. Okay. This is the RHS, this is the RHS, and LHS remains this, LHS remains this. Okay. So now we can write it as product of minus of Biotz number into another dimensionless number, which is very important, that is Fourier's number. So Biotz number we have already seen, that is HLC by K, where LC is the characteristic length, and the Fourier's number is written here. It is alpha tau by LC square, and alpha is same that we have seen in the previous video of while we were deriving the 3D conduction equation. So that is basically thermal diffusivity. Okay. Now let us do a numerical. A steel ball 5 centimeters dia, initially at a uniform temperature of 450 degrees Celsius, is suddenly placed in an environment at 100 degrees Celsius, full stop. Heat transfer coefficient H between the steel ball and the fluid is 10 watts per meter square Kelvin, full stop. For steel, take these properties like Cp is equals to 0.46 kilojoules per kilogram Kelvin, density is 7800 kg per meter cube, thermal conductivity is 35 watts per meter Kelvin. So what you need to do is calculate the time required for the ball to reach a temperature of 150 degrees Celsius. So you can see the ball is actually cooling down from 450 degrees Celsius to 100 degrees Celsius, and we will be calculating time for a temperature which is in between 450 and 100. So we will be calculating time for 150. Okay, so that is clear. So we are calculating time. So when you are asked to calculate time, you are being actually asked to implement the transient heat. But whether you will be implementing the Biotz number means the lumped analysis, or you will go for a graphical method, that you will see after checking the Biotz number. This is the given, the radius of steel ball is given, the density is given, the specific heat is given, the conductivity is given, and the initial temperature Ti is 450 degrees Celsius, the T ambient is 100 degrees Celsius, and the H is 10 watts per meter square Kelvin. Okay. So area of a sphere, you know, that is 4 pi r square. Okay. And volume. Why we are doing this? Because we need to calculate Biotz number, and Biotz number has LC, that is HLC by K, this LC is characteristic length, which is volume upon area. So we need to calculate volume and we also need to calculate area. Okay. So first calculate Biotz number. As I've already told you, this is the checking criteria. So you need to calculate the Biotz number first. So you can see that this HLC by K, so it is like H by K and volume upon area. So it is Biotz number. So Biotz number, what you are getting is definitely lesser than 0.1 here. See, it is definitely lesser than 0.1. And since we have confirmed that the Biotz number is lesser than 0.1, so that means we can now apply lumped system analysis. Okay, this is, I'm again and again telling you, this is the first thing you need to solve until and unless it is stated in the numerical that you need to implement lumped system analysis. Okay, and if it is not written there, then you need to first of all check the Biotz number, and if it is lesser than 0.1, go with lumped system analysis. Okay, now we know the lumped system analysis formula. This is the lumped system analysis formula, that is T minus Ta by Ti minus Ta is equals to e to the power minus Ha tau by rho Cpv. Okay, so everything is given here. Okay, so just calculate the time. Everything is given. See, rho is given, Cp is given, volume we have already calculated, H is given, A is given, everything is given. So just calculate. So when you have calculated time, so the time is 2990 seconds. Okay, did you get this? So where tau is the time to reach. This is the time constant. This is the time constant. So what you need to do, see, the time constant I have already told you, that is rho Cpv by Ha. Okay, so this is the time constant. So since you have calculated this and we know that the unit is in second, so this is also in second. Now what we need to calculate, so put it here. Okay, put it here, 2990, you need to put it here. Now you need to calculate tau. So how will you do this? See, everything is given 150, 100, 450, 100, because we need to calculate time for reaching 150 degrees Celsius. So T of tau will be 150 degrees Celsius. See, T of tau, this temperature at any time. So we need to calculate time for some temperature, and that some temperature is 150 degrees Celsius. Okay, the ambient temperature is 100 degrees Celsius. The initial temperature of the body was 450 degrees Celsius, and again the ambient temperature is 100 degrees Celsius, and you have already calculated the thermal time constant with this formula. Okay, so you need to calculate the time. So see, this is the mathematical thing, and this is what is the time to reach 150 degrees Celsius. Okay, so if we do it in hours, okay, so you will get 1.6 hours. It will take 1.5 hours, approximately more than 1.5 hours to reach from for that body, for that body having that particular dimension with that particular temperature limits. It will take 1.6 hours to cool from 450 degrees Celsius to 150 degrees Celsius. So you can see that to reach from 450 to 100 degrees Celsius, it will take more than 1.6 hours. Okay. So guys, what we have seen till now, that we have actually seen the criteria for giving lumped parameter analysis. Okay, we have already seen that if the Biotz number is lesser than 0.1, then we can only if the Biotz number is lesser than 0.1, then only we can implement the lumped parameter analysis. Okay, so this is the first checking criteria. So as we have seen in this numerical, that first of all we have checked the Biotz number. So for any given numerical, until and unless it is specified, I'm just repeating this once again, until and unless it is specified that the lumped parameter analysis has to be applied, so the question will be framed in a different way. Okay, so then the Biotz number will then be implemented, will not be required to be implemented because it is already stated. But if it is not, then definitely you will be first calculating the Biotz number, and then you will be checking the Biotz number, and if it is coming lesser than 0.1, as you can already see, lesser than 0.1, then definitely you can implement the lumped system analysis. Now let me tell you guys, suppose if we go back, this was all about theory. So let me just discuss something about the applications. Okay, now let us see this application. Okay, here the heat treatment of engineering components and quenching of ingots, heating of electric irons, heating and cooling of buildings, and freezing of foods. So let me just take one of the examples from this, and as I've already told you, as I'm a HVAC engineer, so I will be taking this particular topic, heating and cooling of buildings. So I hope the theory means the analytical portion is already clear. Okay, so I will be discussing theory. So heating and cooling of buildings. So heating and cooling of buildings means what? Suppose if I draw a building here. Okay, so this building, and suppose if this is the daytime. Okay, so what's happening? What's happening here? First of all, the temperature here is increasing. Temperature here is increasing. So from morning 6 a.m. when there's the minimum in summers, okay, now till 3 p.m. when there's the maximum temperature, the peak temperature, okay, so from 6 a.m. to 3 p.m. the temperature curve is actually increasing. Okay, so if this is the time, from this is 6 and this is 3, so the temperature curve is increasing like this. Okay, this is the temperature. This is the time in this is the temperature initial, and this is the temperature peak. Okay, now what happens is, now this curve won't go steadily to this. Okay, it will actually come down. Now what happens is, now when the temperature, when the sun goes down, then what happens? Then this curve tends to climb down. Now this is again time. Now this is suppose 3 p.m. to 3 a.m. Okay, I'm taking the gap of 12 hours. It's 3 p.m. to 3 a.m. Okay, so it will be like it's actually coming down. So if we plot this here, so this is time. If we plot this here from 6 a.m., say suppose from 6 a.m. to 6 a.m., 24 hours gap. Okay, so it actually climbs like this. Okay, this is the peak temperature. Okay, this is supposed to be the minimum. Okay, so it will be like this. It will be a straight line here. Okay, so this is how the temperature varies. Now can you see, this is not a constant heat, this is not a steady heat. So when there is no steady heat, why to use those formula which are for the steady heat? So definitely we have a formula which is now actually keeping pace with a new concept, that is an unsteady heat transfer. An unsteady heat transfer means it's a transient heat transfer. Okay, now what I need to tell you is, let's do something else. Okay, this is a very common concept that I've already told you. You might be knowing it already, or you might easily picturize into your mind. Okay, very easily. But what's next? What's next? Suppose you are living on this floor. What will you actually see in peak summers? What will you actually see in peak summers? In peak summers, you will actually find that in morning time, the temperatures are lesser. I'm talking about the temperature feeling of the residents. Okay, so in morning time, the temperature is lesser of the room, and in evening time, the temperature is going higher, and this is just the opposite if you look at this curve. In morning to the daytime, in morning to the peak day, the temperature is actually increasing. Okay, and from the daytime to the evening, the temperature is actually decreasing. But what the resident of this particular person, what this resident is feeling inside the room, which has an open terrace, okay, and it's a very common example. You can actually relate it to yourself. You can relate it to every common man who is actually, living in a room which has an open terrace, which has an exposed terrace, okay. So what's happening here? So why the temperature profile is just the opposite of what's happening outside? The temperature profile is just the opposite just because it's not related to this particular topic, but I should discuss this because we have taken this example, and this example has two examples. One I have already discussed here, and the other I'm discussing here, okay. So this is something which is very much important, you should know. This is called thermal storage. This is called thermal storage, okay. So thermal storage is something which concrete has a different thermal storage, and concrete has a different thermal storage, bricks has different kind of thermal storage. So what happens is, since during the night time there was no heat, okay, so that cooler temperatures are being actually stored in the thermal storage. So it actually takes near about 6 to 8 hours to release that particular temperature which is actually colder. So in the morning it is actually, you actually feel colder, while outside, if you go to the outside, the temperatures are actually increasing. Whereas this concrete and this wall, this brick is actually, taking in the heat from the peak daytime and further onwards. And then what happens is, when the night temperatures are coming down, now the concrete or the brick has actually started releasing the heat inside the room. So during the night time you feel miserable, while the night temperatures are settling in the comfortable level outside, okay. Whereas in the daytime, where the temperatures are reaching a miserable level outside, you are actually in a comfortable zone inside in your room, okay. So these two temperature profiles are actually contradicting to each other. So this is a new concept that you should be knowing, and this is the thermal storage. This is an additional thing that I have told you in this topic, because if we do not discuss this, the concept of thermal storage, okay, then we would not be able to finish up this heating and cooling of the buildings, okay. So this thermal storage and heating and cooling of the buildings, this freezing of the foods, heating of electric irons, you know that the iron actually heats up, it doesn't heat up just like this, it takes some time. So till now what we have covered the transient heat conduction, okay, and we have seen that the transient heat conduction depends on time, and all the examples that I have told you, okay, it's all time dependent, okay. And then the examples, okay, and suppose if we take the IC engines, again IC engines also takes time to cool, okay. So we have seen the lumped analysis, okay, lumped analysis where the internal resistance is neglected, and we have done the analysis, okay. We have also done the energy balance equation. We have seen HA by rho CPV. This is a thermal time constant, okay. So we have derived it. I have written it like thermal time constant here, okay. And then we have derived for the Biotz number. See, the Biotz number is very important, as I have already told you. This is a checking criteria, okay. LC is the V by A, okay, here. And then we can write this particular the above this thing formula as minus Biotz number into Fourier's number. Fourier's number is another dimensionless number, is alpha tau by LC square. Now we have seen a numerical, and we have calculated the time for 450 degrees to 100 degrees, okay. We have calculated the time to reach from 450 to 150 degrees Celsius, okay. And this is the numerical that we have done, okay. So see, and we have checked the Biotz number 0.1, then only we can confidently tell that what kind of analysis we go to implement, okay. And then the time constant we have calculated, and after time constant we have calculated the actual time to reach 150 degrees Celsius, okay. So this is the time that we have calculated, 1.6 hours, okay. So this was all about the theory, this was all about the derivation, this was all about the numerical, and I have given you some extra thing that is very much important for your later life if you go for any if you opt for the career of thermal engineering, that is the thermal storage. Okay. So, so I think this video was quite useful if you are covering for. So I think this is quite exhaustive video for this time for this particular topic. Okay. So I think this video would actually cater to solve this portion of the unit 2, which is lumped parameter analysis, the theory, the derivation, the numerical, okay, and the little tip that was the thermal storage. So students, have a great day and thank you.